Hi, this is Professor Stugard, and in this video we're going to talk about how we can describe regions in two dimensions. So let's first start with the one-dimensional case. And this is where we're given a variable that's just bounded on either side. In this case, let's take a look at the inequality 1 less than or equal to x less than or equal to 4. And this is a compound inequality because we have those inequality signs on both sides of my variable x. And of course, we know that this means that x is going to take on every single value between 1 and 4, including the endpoints 1 and 4. And a number line, obviously we would draw this as just, well, every single value in between 1 and 4. So 1, 2, 3, 3.5, right, and so on. Now, in two-dimensional space, that same compound inequality, 1 less than or equal to x less than or equal to 4, represents a region that contains every single ordered pair on my xy plane where the x coordinate of that ordered pair is between 1 and 4. The y, there's no bounds on y here, so it extends infinitely in that y direction. Now, what we're concerned about are bounded regions, and the simplest definition for a bounded region is simply a region that is not infinite. So obviously this one is not bounded because it extends infinitely in the y direction. We want bounded regions. So let's look at an example. Let's say we have the region D, and again, we typically use D to describe our general regions in our two-dimensional system. And so let's say we're bounded by that same compound inequality, 1 less than or equal to x less than or equal to 4, but also bounded by the inequality negative 1 less than or equal to y less than or equal to 1. So now we're bounding the x and the y coordinates, and that's going to look like this. So again, we start with our x bounds between 1 and 4, and then I draw the bounds for y. So now I'm drawing those vertical bounds between negative 1 and 1. And the region D is going to be the overlap or the intersection of these two inequalities. So hopefully we can see that this is going to be that rectangle right there. And that will be my region D. And any region that's bounded numerically is going to be a rectangle. And hopefully we can kind of see why that is intuitively, right? If I switched up those values on either side of x or y, as long as they're constants, it's just going to shift and stretch and shrink my rectangle there for my region D. Now, when we integrate over regions, I know that last one is pretty simple because it's just a rectangle, but what we want to do is make sure we consider our x and our y carefully. Now, remember, x is always our horizontal, and so always think x is going from left to right, and y is our vertical, always going from up and down. And I know that sounds really, really simple, but it's one of those key concepts that we need to keep in mind no matter how complicated our region gets. Now, when we set up our iterated integrals, which is really the point of all this, one of our variables is always going to be bounded by numerical constants. If it is a type 1, then my x variable is bounded by constants, and if it's a type 2, that means my y variable is going to be bounded by constants. So let's take a look at an example. Let's say I want to consider this region bounded by 0 less than or equal to x less than or equal to 1, and then y is bounded by 0 and the square root of 1 minus x squared. Well, what is this going to look like? Well, always start with the numeric part first. So I know that x is bounded between 0 and 1. That's the easy part. I know that I'm going to be bounded in this region of my xy plane, right? Between 0 and 1, that extends infinitely, and then y should bound this further. Now, to bound y, okay, 0 is pretty easy. I know that that's going to just be my axis, right? When y equals 0, that's my x-axis. And then my other function, well, if we don't know it, you could obviously just graph it and use technology, or hopefully we recognize that that is half of our equation of the unit circle. Y equals the square root of 1 minus x squared is half of a unit circle. And so it is important to recognize that, and one of those things that, again, you should hopefully be on the lookout, one of those things that whenever you see that function should trigger, oh, maybe this is a circle. And you can do the algebra pretty quick to show why that is the unit circle. So if you start with the x squared plus y squared equals 1, can you get to that thing with the radical? Well, I sure hope so at this point. All right, so what is my region D going to be? Well, it's the overlap of these two. And again, hopefully we can see through this drawing that that overlap is going to be kind of that semicircle part right there. My region D, my overlap, is that quarter of a circle. And again, always take the time to label that region D. Now, is this a type 1 or a type 2? Well, since x is the one bounded by my constants, that makes this a type 1 region. And again, that means that x is extending the entire way. I'm plugging in every value of x from x equals 0 to x equals 1. I'm plugging in every single value from 0 to 1. And then the top of that bound is going to be my y. And again, that height y is going to vary based upon that inequality. It's always going to have a lower bound of 0, and then the upper bound is determined by that function right there. And hopefully we can see that as we change our values of x, that height is going to change. And again, that's why y is bounded by a variable function. That height, in this case, is going to vary as we move left and right with my values of x. The height y changes. All right, let's try another region. Let's consider the region bounded by 1 less than or equal to y less than or equal to 2, and then y less than or equal to x less than or equal to y cubed. Now, wait a second. Look at that bottom inequality. Well, in this case, x is now being bounded by functions of y. Or we would write x equals f of y. Now, does this change anything? Well, it changes the way we might look at it slightly, but really it's the same exact process. We just need to be careful. Now, if you're trying to use your calculator to graph, well, you might want to find the inverses to help you graph what this is going to look like. All right. But as always, we start with our bounds that are constant. So I know y is between 1 and 2, so there we go. That's what y between 1 and 2 looks like. And now I need to figure out what those other two functions are going to look like. So that y is less than or equal to x. Well, what I want to really graph is x equals y, or y equals x. Now, again, the inverse there is pretty straightforward, so it's kind of the same thing. The other one is a little bit trickier, because if I have x equals y cubed, the inverse there is going to be y equals the cubed root of x. And hopefully we can go back and forth with the inverses, and that's not really a problem here. And so I see I have these two functions, and so inside that value for y, right, in that region where y is between 1 and 2, what part is bounded between those two functions that I just drew? Well, again, hopefully we can kind of see that it's going to be this region I just shaded with the d in it. All right. This is a type 2 inequality because y is the one bounded by constants now, and x is going to vary depending on the top and bottom. Okay, now what we want to be able to do is take these ideas and now be able to describe regions that aren't necessarily described with my inequalities. So how could I describe this region bounded in the first quadrant by y equals x and y equals x squared? Well, first of all, we need to make sure we understand what the first quadrant is, or quadrant 1. And of course, quadrant 1 is when x is greater than 0, greater than or equal to 0, and y is greater than or equal to 0. Right, we have just positive values for x and y. And what is that region that's going to be bounded? Okay, so let's graph our two lines. We have y equals x and y equals x squared. Well, where's the bounded part in this particular picture? Well, the bounded part is just that region right there. Right, that's the part that's bounded. There's my region D. Right, that's the only part where it is closed and not infinite, not extending out to infinity. So now I need to describe this region using either a type 1 or a type 2, and spoiler alert, let's do both. But let's start with a type 1. So type 1, that means we need to bound x by a constant first. So we just look at this picture and we look, okay, well, what values of x does this entire region take on? Well, it starts at x equals 0, goes up to x equals 1, right? And again, very general, takes on from x equals 0 to x equals 1. So we get the compound inequality 0 less than equal to x less than equal to 1. Now the more tricky part is going to be then bounding y. So y needs to be bounded by functions of x. So how am I going to do that? Well, this is where, again, draw that arrow, that two-directional arrow, so that we see what is y going to actually look like in the context of this region. Always draw kind of a sample arrow, or maybe even a sample rectangle if you're used to finding like volume problems or something like that. But draw that sample, and then consider, okay, well, what's going to be on the top and what's going to be on the bottom? Well, it's bounded on the bottom, that bottom of my my arrow for y, that's my function y equals x squared, and the top, or where it's bounded above, is bounded by y equals x. So I need to make sure that I preserve that inequality when I write it out. So the bottom is the x squared, so it'll be x squared is less than or equal to y which is less than or equal to x. And that's how I would describe this as my type 1 region. Always a good idea, right? I drew that arrow in one spot. Draw it somewhere else. Check across the region. Make sure that the bounds are same throughout the shape. Now, again, they shouldn't change unless the curves actually intersect each other, but it never hurts to double check, right? It's better to take that extra time and be right than to be wrong very quickly. Okay, let's go back to this region. Now let's try to bound this as a type 2. And by a type 2, that means we need to bound y by constants first. Now, in this case, I can see that that region takes on y coordinates that vary from 0 to 1. So y is bounded between 0 and 1. Now, how am I going to bound x? Well, again, start by drawing that arrow. Now, x is my horizontal, so how am I getting from one point to the other? All right, well, now I need to be able to describe these functions, except, right, I need to bound my x variable by functions of y. So I'm going to have to do that inverse thing again. Now, the top one is easy. Y equals x is x equals y. There's no change there. And the y equals x squared, if I have to solve that for x, that's going to be x equals the square root of y, right? Just take the square root of both sides. Now we got to figure out which one's the top and which one's the bottom. And it's a little bit more difficult when we do our type 2s. For some reason, it's just not as intuitive. And we want to be really careful to make sure we know which is the top and which is the bottom of this particular region. So to determine the upper and lower bounds in terms of x, the easiest thing to do is just rotate your paper. So let's turn it. My same region now to determine those upper and lower bounds. Well, let's see, which one's on the bottom? Well, now I can see that on the bottom is my line y equals x, or, well, since I need to do this in terms of y, it's my line x equals y. And on the top, it's going to be my curve x equals the square root of y. So when I write my inequality and flip my paper back the right way, I'll have y is less than or equal to x, which is less than or equal to the square root of y. All right, so those are the examples I wanted to run through. A few keys to success in being able to describe your regions, which if you can't even describe your region, you're not going to be able to set up your integral, and you're basically not going to be able to do the rest of the problem. So understanding this first step is pretty critical. Step number 1, make large drawings. Use technology if you need to see the graphs if you don't know exactly what they look like. But make those large drawings, sketch it all out, use technology if you need to, because there are some times where these functions can get really tight together, and if you don't see what's going on, you'll absolutely set up your bounds wrong. So also make sure that with that large drawing, you clearly mark where all of the curves intersect and find those intersection points, because we might have to change the bounds there, or it'll just be our bounds. And then also try to remember that always one variable is going to be bounded by constants, and see which one that is. Now, sometimes it's obvious, sometimes it's not. Sometimes you could choose either one, and without any real loss of generality. Sometimes it'll depend on the integration, so we got to be able to switch between type 1 and type 2 anyway, because sometimes your integrand might be unintegrable because there's no antiderivative to that function. But if you swap the variables and do it in terms of the other one, then you might have a solution there. But remember, one of them is always going to be bounded by constants, and then the other region, or the other variable, I'm sorry, is going to be bounded by the functions. Now, unless that region is a rectangle, in which case everything's numeric, but the only time it's always numeric is if it's a rectangle. So unless that shape is a rectangle, I do not want to see numbers for both sets of bounds. All right, that takes care of it for this video. So good luck studying, practice drawing those regions, draw big, mark it clear, and good luck. Take care of yourselves.